Hello, and welcome to the Snoozy Scientist. I'm really glad you made it here tonight. Wherever you are on this planet, this little pocket of quiet was made just for you. A calm space where science and stillness can sit side by side. Tonight, we're going to drift slowly into a story that feels almost too big to imagine. A story about the sun, our life giver, and the other, wilder side it hides. The sun gives us warmth. It makes the air breathable, the oceans liquid, and the soil fertile, but it also hides a violent, unpredictable temper, one that could erase centuries of human progress in mere minutes. And throughout history, it has reminded us. These reminders come as massive solar storms, powerful enough to engulf our whole planet, the kind you hope never to experience in your lifetime. Scientists have found evidence of more than a dozen significant ones over the last 500 years. The last great storm humans actually saw was in the year 1859, the Carrington Event. And more recently, in 2012, we came terrifyingly close. A storm of staggering power erupted from the sun and crossed the exact spot where Earth had been just 9 days earlier. NASA scientists say that if it had struck, it could have set our civilization back 100 years. The impact would have destroyed all our satellites, crippled all power grids, plunged billions into darkness, and ended global communication in minutes. Imagine phones and computers around the world shutting down without warning, airplanes, mid-flight, falling eerily silent as their instruments go dark. And above it all, the sun hanging swollen and blazing, spitting arcs of fire toward Earth. We got lucky in 2012. Our ancestors were not always so fortunate. In the year 774 AD, a storm struck with such force that its signature is still locked inside the rings of ancient trees. Another came 2 centuries later, leaving its mark deep in the ice of Greenland and Antarctica. Even these pale in comparison to the prehistoric superflares, eruptions hundreds of times more powerful than anything humanity has ever witnessed. Evidence shows that, long before humans ever walked the Earth, massive solar eruptions may have scorched the planet, altered climates, and changed the course of evolution. Tonight, we'll journey through all of them, from the events our ancestors survived to the cataclysms that came long before us, to understand just how close we have come to losing it all. And by the end, you may realize that the question isn't if the sun will remind us again, but when. If you're already feeling the calm, it would mean the world if you gave this video a gentle like, maybe even subscribed if you'd like more sleepy science stories like this one. And if you'd be so kind, let me know in the comments, where are you winding down from tonight, and what time is it there? It always brings me joy to see how far these gentle science stories manage to ripple out across the globe. So now, take a slow breath, let your shoulders drop, and let's begin. The sun sits at the very center of our solar system, a blazing sphere of energy that has shaped every moment of Earth's history. Without it, there would be no oceans, no forests, no living breath in the air. The sun fuels life in ways so constant and familiar that we rarely stop to notice them. Its light warms the soil where seeds take root. It powers the photosynthesis that turns leaves into living factories, and it drives the weather systems that carry water from the seas to the mountains and back again. Every heartbeat, every gust of wind, every drop of rain is in some way a gift from the sun. Yet this same star is not gentle by nature. The sun is a seething ball of plasma, its surface alive with motion, its heat and light born from deep within. At its very center lies the core, the heart of the sun, where temperatures soar to millions of degrees. Here, under immense pressure, hydrogen atoms are forced together to form helium, releasing staggering amounts of energy in the process. This nuclear fusion is the engine of the sun, producing the light and heat that radiate outward into the solar system. Beyond the core lies the radiative zone, a region so dense that the light produced at the center takes hundreds of thousands of years to escape. Photons, the particles of light, are absorbed and re-emitted countless times as they inch their way toward the surface. It is a slow, meandering journey, the energy passing from particle to particle like a secret carried through a vast and crowded room. After the radiative zone comes the convective zone, where the temperature drops enough for currents of plasma to begin to churn. Hot material rises toward the surface, while cooler material sinks back down, creating a constant boiling motion. These immense convection currents are like the slow, powerful stirrings of an ocean, made not of water, but of glowing gas. The photosphere is what we think of as the surface of the sun, though in reality it is not solid at all. It is a thin, bright layer from which most of the sun's visible light escapes into space. Sunspots, darker and cooler than their surroundings, appear here as shifting shadows on the surface. Above this is the chromosphere, a layer that glows faintly red, and beyond that lies the corona, the sun's outer atmosphere, stretching millions of kilometers into space. The corona is strangely hotter than the layers below it, a puzzle that scientists are still working to fully understand. It is from the corona that solar wind streams outward, carrying charged particles across the solar system. For billions of years, the sun has burned steadily enough to allow life to flourish on Earth. This stability is part of what makes our planet so rare, a delicate balance between the immense forces at the sun's heart and the thin veil of atmosphere that protects us from its full intensity. Yet the sun is not unchanging. Its surface can erupt in solar flares, massive bursts of energy that can hurl billions of tons of charged particles into space. These events are part of its nature, born from the same magnetic forces that shape its beauty. It is this paradox, the sun as both a gentle life giver and a potential destroyer, that makes it such a powerful presence in our story. From the warm light on a spring morning to the violent storms that can ripple through space, the sun's influence reaches every corner of our world. Understanding its structure and its temperament is not simply a matter of astronomy. It is a way of understanding the fragile conditions that make life possible and the forces that could, in an instant, threaten it. And it is here, with this awareness of the sun's true nature, that we begin to see how the same star that cradles life in its light can also unleash events that test the limits of human resilience. In the late summer of 1859, the sun performed a display so powerful and strange that it would leave its mark on scientific history forever. On the morning of September 1st, a man named Richard Carrington, a dedicated amateur astronomer in England, was at his telescope. The air was still and quiet, the way it often is before something extraordinary. Carrington was sketching a cluster of sunspots when, without warning, he saw a blinding flash of intense white light erupt from the surface. It was not like the flickering of the atmosphere or the slow changes he was used to observing. This was sharp and violent, a sudden burst that seemed to pierce through the calm face of the sun. What Carrington witnessed was a white light solar flare, a rare and powerful explosion of energy that hurled vast amounts of charged particles out into space. At the time, no one truly understood the mechanics of what he had seen. Yet within hours, the effects of this event began to ripple across the earth in ways that people could not ignore. By the following night, the sky came alive. Auroras blazed not just over the polar regions where they usually dance, but far into the tropics. People in the Caribbean reported crimson and green curtains sweeping across the heavens. In the Rocky Mountains, miners were woken by the glow, thinking it was dawn. The light was so bright in some places that birds began to sing, and newspapers could be read outdoors in the middle of the night. For many, it was a thing of wonder, a rare and beautiful gift. But for those who worked with the world's young electrical systems, it was something far more alarming. Across Europe and North America, telegraph systems began to fail in ways no one had seen before. Operators found that their equipment was sparking violently. Some telegraph lines caught fire, the wood and paper in their offices smoldering from the sudden surges of electrical current. Messages could be sent even after the power supplies were disconnected, carried entirely by the energy flowing through the atmosphere itself. To the people of the time, it was both fascinating and terrifying, as if invisible lightning had wrapped itself around the world. The cause of this chaos was a massive coronal mass ejection, a cloud of charged particles blasted from the sun directly toward Earth. When this wave struck the planet's magnetic field, it compressed and twisted it, driving powerful currents into the ground and into anything made of metal. In 1859, the most advanced technology on Earth was the telegraph. The damage was disruptive but recoverable. Life went on. It is difficult to imagine what would happen if an event of this magnitude struck in our own time. Our world is laced with electrical systems, woven through with satellites, communication networks, and power grids that span continents. A storm like the Carrington Event today would not simply make auroras dance over the tropics. It could blind satellites in orbit, sever the cables that carry the internet across oceans, and cause transformers and power stations to fail in a cascade that could leave millions without electricity for weeks or even months. Air traffic could halt, navigation systems could collapse, and the quiet hum of modern life could be replaced by an eerie stillness. The Carrington Event was a warning written in light across the sky, a reminder of how closely tied we are to the moods of our star. At the time, humanity saw only a glimpse of what such a storm could do. In our interconnected age, the scale of its impact would be far greater, a chain reaction felt in every corner of the globe. As Richard Carrington stood at his telescope that morning, he could not have imagined that the flash he had sketched would become a symbol for one of the most powerful solar storms in recorded history, or how deeply relevant it would remain for the generations to come. A solar storm begins on the surface of the sun, but its effects can be felt across the vast gulf of space and all the way down to the surface of the Earth. To understand what a solar storm is, we need to break it down into its different forms, because not all solar disturbances are the same. The most familiar kind is the solar flare. A solar flare is a sudden, intense burst of radiation that comes from the release of magnetic energy near sunspots. It is like a flashbulb going off in the atmosphere of the sun, but on a scale so enormous that the light and X-rays it produces can travel across the 93 million miles to Earth in just over 8 minutes. This radiation can disrupt communication signals and affect satellites almost immediately after the flare occurs. Another type of solar storm is a coronal mass ejection, often called a CME. While a solar flare is a burst of light and radiation, a CME is a giant bubble of plasma and magnetic field that is thrown out from the sun into space. These clouds can contain billions of tons of charged particles, and they move more slowly than the light from a flare, taking anywhere from 1 to several days to reach Earth. If a CME happens to be directed toward our planet, it can cause the magnetic field around Earth to compress and ripple, creating the spectacular auroras we see in the sky, but also inducing powerful electric currents that can damage electrical systems on the ground. There is also a third category called solar energetic particles. These are high-energy protons and other atomic particles that are accelerated by solar flares, or CMEs, to nearly the speed of light. They can arrive at Earth within minutes to hours of being launched from the Sunday. These particles are particularly dangerous for astronauts outside the protection of Earth's magnetic field, and they can also pose risks to spacecraft electronics and high-altitude flights over the poles. The impact of any solar storm depends on three main factors: The first is speed. The faster a CME or stream of particles arrives, the less time we have to prepare. Some of the most powerful CMEs have raced toward Earth in less than 18 hours. The second factor is intensity. This is a measure of how much energy and how many particles the storm carries. A smaller CME may pass by with little effect, while a massive one can cause widespread technological disruption. The third factor is direction. The sun constantly throws material into space, but most of it misses Earth entirely. For a storm to cause trouble, it must be aimed directly at our planet, and the magnetic orientation of the CME must be just right to interact strongly with Earth's magnetic field. The origins of these storms often lie in dark patches on the sun called sunspots. Sunspots are areas where magnetic fields are twisted and concentrated, making them cooler and darker than the surrounding surface. These magnetic fields can snap and reconnect, releasing energy in the form of flares and CMEs. Sunspot activity follows an approximately 11-year cycle, moving from a solar minimum with few sunspots to a solar maximum where the sun's surface is speckled with them. During solar maximum, the chances of strong storms increase because the sun's magnetic field is at its most tangled and active. By watching the sun closely and tracking the growth and movement of sunspots, scientists can sometimes forecast when the conditions are ripe for a solar storm. Spacecraft like the Solar Dynamics Observatory and the Parker Solar Probe feed us images and measurements, helping us understand the sun's behavior in greater detail. This constant observation is our first line of defense, because while the sun's storms are born 93 million miles away, their reach is long, and their effects can be felt in the invisible currents flowing through the technology we depend on every day. In March of 1989, the sun sent a reminder that even in our modern world, with all its engineering and technology, we are still vulnerable to the forces of nature. It began quietly, in the depths of space, as a massive coronal mass ejection left the surface of the sun and began its journey toward Earth. The cloud of charged particles sped through the darkness for more than 3 days before finally slamming into our planet's magnetic field on March 13th. High above the ground, the collision sent waves rippling through the magnetosphere, twisting and compressing it. These magnetic disturbances race through the atmosphere and into the Earth's crust, generating electric currents over vast areas. Normally, these currents are weak and pass unnoticed, but the storm of 1989 was different. The strength of the disturbance was enough to push huge surges of current through the network of high-voltage transmission lines that carried electricity across large distances in Canada and the northern United States. In Quebec, the electrical grid was especially vulnerable. Hydro-Quebec's system relied on long transmission lines that stretched over hundreds of miles, anchored in the solid, resistive rock of the Canadian Shield. This geology, combined with the intensity of the geomagnetic storm, turned the grid into a giant antenna for the invisible energy pouring out of space. At 2:44 in the morning, control room operators began to see signs of trouble. Warning lights flashed and alarms sounded as transformers overloaded and protective systems tripped. Within less than 2 minutes, the entire provincial power grid collapsed. Quebec went dark. The blackout happened at the tail end of winter, and the temperatures were well below freezing. Streetlights went out. Homes, businesses, and entire neighborhoods were suddenly without heat. In some places, the only illumination came from the eerie glow of the auroras, shimmering green and red overhead, bright enough to be seen far to the south of their usual range. For 9 long hours, Hydro-Quebec struggled to bring the system back online. People wrapped themselves in blankets and lit candles. In high-rise apartments, the loss of elevators and heating systems was more than an inconvenience. It was a dangerous situation for the elderly and for anyone with medical needs. Communications were disrupted, and in some areas, even water systems were affected because pumps had no power. The storm did not just affect Quebec. Transformers in New Jersey were damaged, and electrical disturbances were recorded as far away as the United Kingdom. Satellites in orbit experienced glitches, and some temporarily lost contact with ground stations. Airline flights were rerouted to avoid high-latitude paths where radiation levels were elevated. For governments and scientists, the 1989 blackout was a wake-up call. It was the first time in the modern technological era that a geomagnetic storm had caused a major power grid to fail on such a scale. It showed that the systems we depend on are deeply interconnected, and that a disturbance in space can trigger cascading failures here on Earth in a matter of moments. In the years that followed, studies were launched to understand how to protect grids from similar events. Utilities began to install monitoring equipment that could detect the slow buildup of geomagnetically induced currents. Operators were trained to take emergency measures if the space weather forecast predicted a major solar storm. The 1989 blackout also pushed agencies like NASA and the National Oceanic and Atmospheric Administration to expand solar monitoring programs so that warnings could be issued with hours, or at least minutes, of lead time. The lesson from that night was clear to those who experienced it. The sun is not simply a distant, unchanging ball of light in the sky. It is active, restless, and capable of reaching across millions of miles to disrupt life in an instant. The blackout in Quebec was over by mid-afternoon, but the knowledge of how quickly it happened and how easily it could happen again stayed with those who lived through it, and with those responsible for keeping the lights on in a world that depends more than ever on electricity. High above the surface of our planet, far beyond the clouds and the blue of the sky, an invisible guardian is always at work. This is Earth's magnetic shield, known to scientists as the magnetosphere. It stretches thousands of kilometers into space in all directions, forming a protective bubble around our world. Without it, life as we know it would be constantly bombarded by streams of high-energy particles from the sun and from distant parts of the galaxy. The magnetosphere begins deep inside the Earth, in the molten outer core. Here, iron and nickel swirl in slow, powerful currents, driven by heat from the planet's interior. These moving metals create electric currents, and those currents generate a magnetic field. This field extends outward, shaping the space around our planet. On the side facing the sun, the field is compressed by the constant push of the solar wind, forming a blunt, rounded edge. On the side facing away from the sun, it stretches far into space like a long tail, sometimes reaching beyond the orbit of the moon. When charged particles from the solar wind arrive at Earth, most are deflected by this magnetic barrier. They are guided around the planet, following the curved lines of the field. This deflection is vital because without it, the constant stream of particles would strip away the atmosphere and expose the surface to harmful radiation. Planets without strong magnetic fields, like Mars, offer a sobering comparison. Mars once had a thicker atmosphere and possibly liquid water on its surface, but without a global magnetic shield, the solar wind slowly eroded its protective layers, leaving behind the thin, fragile atmosphere it has today. Yet the magnetosphere is not an impenetrable wall. When a solar storm arrives, especially a coronal mass ejection carrying its own magnetic field, the interaction can become complex and dangerous. If the magnetic field carried by the storm is oriented in the opposite direction to Earth's magnetic field, they can connect in a process called magnetic reconnection. This opens a pathway for solar particles to pour into the magnetosphere, driving energy deep into the system. The impact compresses the day side of the magnetosphere and sends waves racing down its tail, triggering geomagnetic storms. When these storms occur, particles spiral down along magnetic field lines toward the poles, colliding with atoms and molecules in the upper atmosphere. The energy from these collisions excites the gases, causing them to glow. This is the origin of the auroras, the shimmering curtains of green, red, purple, and blue that dance across the polar skies. During strong storms, these lights can be seen far from the poles, sometimes even in regions that rarely experience them. To the eye, they are beautiful, almost magical. But to scientists, they are also warnings, a visible sign that the sun has reached across space and disturbed our magnetic shield. While auroras are the most visible sign of a magnetospheric disturbance, much of the action takes place silently and invisibly. Magnetic storms can induce powerful electrical currents in the ground and in man-made systems like power grids. Satellites in orbit can be exposed to higher levels of radiation, leading to malfunctions or even permanent damage. Communication systems can experience interference, and navigation signals can become unreliable. The magnetosphere is constantly changing, flexing and shifting in response to the sun's activity. Spacecraft, such as NASA's Themis mission and the European Space Agency's cluster satellites, study these changes in detail, helping scientists understand how energy from the sun flows through our magnetic environment. This knowledge is crucial for predicting space weather and for protecting the technology that modern life depends on. From the surface of the Earth, we rarely think about the shield above us. It works in silence, unseen, its presence felt only in the gentle steadiness of the environment we take for granted. Yet each time the auroras glow and ripple across the night sky, they remind us that our magnetic guardian is engaged in a constant, delicate battle with the forces of the sun, turning what could be a destructive storm into a dazzling light show before the danger passes deeper into the night. In the quiet forests of Japan, ancient cedar trees have stood for centuries, their trunks slowly growing wider with each passing year. Each ring within their wood is a record of the conditions in which the tree lived, a thin, fragile archive of climate, rainfall, and even events far beyond Earth's atmosphere. In the early 21st century, scientists studying these rings made an unexpected discovery. When they measured the amount of carbon-14, a radioactive form of carbon that forms when cosmic radiation strikes the atmosphere, they noticed a sudden and dramatic spike. It was not a gradual change that could be explained by shifting climate or seasonal variations. It was abrupt and intense, pointing to an extraordinary burst of high-energy particles striking Earth sometime between the years 774 and 775 AD. This increase in carbon-14 was not confined to one forest or one part of the world. The same signal appeared in tree ring samples from Europe, North America, and New Zealand. It was as if the entire planet had been bathed in a sudden shower of cosmic radiation. To confirm this, scientists turned to another archive of Earth's past, the layers of ice preserved in Greenland and Antarctica. These ice cores, drilled from deep within glaciers, contain trapped bubbles of ancient air and chemical traces of atmospheric events. In the layers corresponding to the same years, they found elevated levels of beryllium-10, another isotope created by cosmic particle bombardment. Together, these two lines of evidence pointed to a massive solar proton event, far more powerful than anything measured in the modern era. Solar proton events occur when the sun hurls a storm of high-energy protons into space. If Earth is in the path, those particles can penetrate the upper atmosphere, triggering chemical reactions and producing the isotopes found in tree rings and ice cores. The intensity of the 774 event suggests it was several times stronger than the largest solar storms recorded with instruments. There are hints that people at the time may have noticed something strange. Historical accounts from the Anglo-Saxon Chronicle, a record of early medieval England, mention a red crucifix appearing in the sky after sunset in the year 775. In China, ancient texts describe unusual red lights stretching across the heavens. While the exact descriptions are open to interpretation, these sightings could have been auroras, sparked by the storm, appearing much farther from the poles than usual. To those living in the early Middle Ages, without any understanding of the sun's behavior, such lights may have seemed like omens, signs from the divine, or warnings of events to come. A similar episode occurred more than 2 centuries later, between 993 and 994 AD. Once again, carbon-14 levels in tree rings jumped sharply, and ice cores showed matching increases in beryllium-10. These signatures point to another intense burst of solar particles slamming into the atmosphere. Though fewer historical records survive from that time, there are scattered references in East Asian chronicles to strange lights in the sky, described as heaven's fire. In both cases, the storms were strong enough to leave a measurable fingerprint across the entire planet, yet they happened in an age without electrical grids, satellites, or radio communications. If events of this magnitude were to occur today, they could disrupt technology on a global scale, damaging satellites, endangering astronauts, and possibly causing widespread power outages. The medieval observers saw only the beauty and mystery of the lights in the sky, unaware that they were witnessing the visible edge of a much larger storm arriving from 93 million miles away. These ancient bursts remain some of the strongest solar events known to science, revealed not through photographs or instruments, but through the patient work of trees and ice, quietly keeping their record for more than 1,000 years until someone learned how to read it. And just as the layers of wood and ice carry those stories forward through time, the energy that caused them was carried across space, a reminder that the sun has always been capable of far more than the calm, steady glow we see each day. Across the world, in stories passed down through generations, the sun is often more than a source of warmth and light. In the myths of many ancient civilizations, it is a living presence with moods, desires, and tempers. Some traditions speak of the sun as a benevolent giver of life, while others describe it as a force capable of terrible wrath. In certain legends, the sun grows angry and the skies ignite with strange colors, a sign that the balance between the heavens and the earth has been disturbed. These tales, told long before people understood the science of solar storms, may have been inspired by real events that left a deep impression on those who witnessed them. In parts of the Pacific, there are oral histories describing days when the sky turned red and glowing shapes moved across the night. In Norse mythology, there are references to the sun being chased across the sky by a great wolf, sometimes caught and swallowed, plunging the world into darkness before returning. The Aztecs spoke of different suns ruling the world in past ages, each one ending in a catastrophe, some of which involved fire falling from the sky. Even in the records of ancient China, court historians documented nights when crimson light stretched across the heavens, an event often interpreted as a sign of political or cosmic change. While such descriptions are wrapped in symbolism and shaped by cultural beliefs, some of them match what we now know can happen during intense geomagnetic storms. Auroras pushed far from the poles can bathe the night in red, green, or purple light, shifting and shimmering in ways that would seem otherworldly to anyone who had never seen them before. Without the language of space weather or magnetospheres, ancient peoples would have explained these visions through the stories and beliefs that shaped their world. The sun's importance was not only spiritual or symbolic. Many ancient societies tracked its movements with remarkable precision, building structures and monuments aligned to its yearly cycle. At Stonehenge in England, massive stones are arranged so that on the summer solstice, the rising sun lines up perfectly with the central axis of the monument. In the deserts of Peru, the lines and shapes of the Nazca geoglyphs are believed by some researchers to be aligned with the sun's position at certain times of the year. In ancient Egypt, temples were constructed so that on specific days, sunlight would pierce deep into their inner chambers, illuminating statues of gods or pharaohs. The Maya, masters of astronomical observation, built entire cities with pyramids and plazas oriented to mark solstices and equinoxes. Their calendar systems were tied to the sun's apparent path, and they kept detailed records of celestial events. Similar alignments can be found in the ruins of Chaco Canyon in North America, where windows and petroglyphs were positioned to track the sun's journey. These alignments were vital for agriculture, helping communities know when to plant and harvest, but they may have served another purpose as well. If extraordinary solar events had been witnessed in the past, with strange lights filling the skies or the sun behaving in unexpected ways, tracking its patterns could have been a way to watch for signs of such occurrences returning. This raises the question of whether some myths of angry suns and skies on fire are not only symbolic tales, but fragments of cultural memory carried forward in story, song, and stone. From the frozen tundra to the equatorial plains, the sun has been humanity's constant companion, its daily rising and setting marking the rhythm of life. For those who lived thousands of years ago, its rare and dramatic changes would have been unforgettable, worthy of carving into rock or weaving into sacred stories. As we move from these ancient monuments and myths toward the scientific explanations we have today, the link between the sun's past displays and the stories that survive may offer a bridge between the worlds of legend and the realities of cosmic weather. In the spring of 1921, the world was still finding its way into the modern age. Telegraph lines crisscrossed continents, carrying urgent messages in dots and dashes. Railways moved people and goods at a pace that would have been unthinkable only a century earlier. Cities glowed at night with the steady light of electric lamps, and the hum of industry was powered by vast, interconnected networks of wires and machines. Few people gave much thought to the fact that all of it, from the telegraph operator's key to the railway signalman's switch, could be silenced by something that began 93 million miles away. In early May, the sun unleashed a powerful solar storm, a massive ejection of charged particles that sped through space toward Earth. When this wave of energy arrived, the effects were felt almost immediately. Telegraph lines began to behave unpredictably, sparking and buzzing with currents that no operator had sent. Across Europe and North America, stations reported bursts of static so intense that normal communication became impossible. Messages were garbled or lost entirely, and in some cases, lines fell silent altogether. In railway control rooms, the trouble was even more alarming. The storm's electrical surges flowed into signaling systems, causing lights to flicker and switches to jam. In some places, signals were stuck on stop, halting trains until the systems could be reset. In others, the signals showed false clear indications, a dangerous condition that forced operators to scramble to ensure that collisions were avoided. The geomagnetically induced currents generated by the storm did not care about timetables or human schedules. They moved silently through every mile of metal track and every wire strung along the route. Reports from that time tell of control room equipment bursting into flames without warning. The surges were strong enough to overheat delicate components, and the smell of burning insulation and wood filled the air in several stations. In Sweden, telegraph offices experienced fires sparked directly by the current in their lines. In the United States, railroad telegraphers described instruments jumping and hissing, the sound of invisible power forcing its way into their work. This storm was powerful enough that its influence was recorded worldwide. In New York City, the disturbances interfered with the stock ticker systems that fed information to brokers, briefly cutting the flow of financial data. In the United Kingdom, transatlantic telegraph cables went down for hours. Across the Pacific, even lines in Australia and Japan reported unusual interference. The reach of the event underscored how interconnected the world had already become, and how a disruption in one part of the globe could echo thousands of miles away. While the telegraph and railway systems eventually returned to normal, the storm of 1921 earned its place in history as the closest rival to the Carrington Event of 1859. Scientists studying the records estimate that its magnetic strength was nearly as great, though its impact was shaped by the different technologies of the era. In a time before satellites and global positioning systems, the main damage was to wired communications and transportation. But the scale of the disruption made it clear that such storms could reach deep into the heart of human activity. The railway storm, as it came to be known in some reports, showed how even robust mechanical systems could be brought to a standstill by space weather, and while the people of 1921 recovered, their experience provided a detailed case study for scientists in later decades, offering clues about what a similar event might do in a world far more dependent on electronics and instant communication. The lessons from that May were preserved in logbooks, engineering reports, and the memories of those who saw fire leap from instruments that had never failed before, a quiet reminder that the sun's reach can extend into every corner of life on Earth. Long before cities lit the night sky and satellites circled above us, the sun still had the power to change the fate of life on Earth in an instant. In the deep past, long before written history, there were moments when our star unleashed explosions so vast that they make the Carrington Event look small by comparison. These were prehistoric superflares, colossal eruptions of energy and particles that left their marks not in photographs or eyewitness accounts, but in the very fabric of the planet itself. Scientists first began to suspect the existence of such ancient storms when studying the strange chemical signatures preserved in ice cores from Greenland and Antarctica. Layer by layer, year by year, snow had fallen and compacted into ice, trapping tiny bubbles of ancient air and preserving delicate traces of chemicals from the atmosphere. In certain layers, researchers found sudden spikes of nitrates and other byproducts of intense solar radiation. These were not gradual changes. They appeared abruptly, standing out like the jagged peaks of a heartbeat on a monitor, hinting at massive bursts of energy that had struck Earth thousands, even tens of thousands of years ago. Geological records told a similar story. Tree rings, some from ancient petrified wood and others from still living trees with centuries of growth, showed abnormal rises in carbon-14. This isotope forms when cosmic rays, or high-energy solar particles slam into our atmosphere, changing the chemistry of nitrogen atoms. A sudden increase in carbon-14 means that something powerful flooded the skies with radiation, while events like the Carrington storm of 1859 can leave a noticeable trace. Some of these prehistoric spikes were hundreds of times stronger. The scale of these superflares is difficult to imagine. If the Carrington event released enough energy to fry telegraph lines across continents, a superflare hundreds of times larger could, in today's world, destroy much of the planet's electrical infrastructure in moments. The blast of charged particles would overwhelm satellites, cripple navigation systems, and plunge large regions into darkness. For ancient Earth, without cities or circuits to burn out, the danger came in other forms. One possible effect of such a colossal storm would be on the planet's climate. A superflare could strip away parts of the ozone layer, allowing more ultraviolet radiation from the sun to reach the surface. This would not just scorch exposed skin, it could damage plant life, particularly the delicate microscopic organisms at the base of ocean food chains. With their ability to absorb sunlight disrupted, entire ecosystems could wobble, leading to ripple effects in weather patterns, food availability, and even global temperatures. For early life, especially in times when complex organisms were just beginning to spread across the continents and oceans, such disruptions could be catastrophic. Some scientists have proposed that certain mysterious gaps in the fossil record might align with the timing of massive solar events detected in geological archives. The theory is that a superflare could act like a sudden, invisible storm, stressing species already living close to the edge of survival. The evidence also points toward the role of solar cycles, much like the ones we track today, but potentially more extreme in the distant past. The young sun was more active, spinning faster and releasing energy more violently. Its magnetic fields twisted and snapped with greater force, making superflares more likely. Over millions of years, the sun has calmed, but traces of its wilder youth remain locked away in ice, rock, and wood, waiting for scientists to uncover them. By piecing together these chemical and geological clues, researchers are slowly revealing a hidden chapter of Earth's story, one written in the language of radiation and magnetic storms. It is a reminder that the relationship between the sun and life on this planet has always been one of both nurture and danger, a delicate balance shaped by forces that can flare without warning. And as these records show, the greatest solar storms are not just a thing of history. We can see they are a part of the planet's deep memory, etched into every layer of its past. When scientists try to peer into the history of the sun's most powerful outbursts, they cannot simply rewind time and watch them unfold. Instead, they turn to the planet's own archives, records written not on paper but in the growth of trees and the layers of ancient ice. Each year, a tree adds a new ring of wood, and with it, a subtle chemical fingerprint of the air and sunlight it experienced. In certain years, those rings show a sudden surge of carbon-14, an isotope that forms when high-energy particles from space strike nitrogen atoms in the atmosphere. These particles could come from a massive solar storm, flooding the upper air with radiation strong enough to change its very chemistry. But trees are only part of the story. Deep in the ice sheets of Greenland and Antarctica lies another kind of record, made not by wood, but by snow that fell thousands of years ago and froze in place. Over centuries, each snowfall trapped tiny amounts of dust and gas from the air. Within these frozen layers, scientists have found spikes in beryllium-10, another isotope created when cosmic particles crash into our planet. These spikes match closely with some of the same years that show unusual carbon 14-inch tree rings, strengthening the case that they were caused by bursts of energy from the sunday. The challenge lies in making sure that what we see in these records really came from solar activity and not from something else entirely. Cosmic rays from distant supernovae, for example, can also trigger the same chemical changes in the atmosphere. So can massive volcanic eruptions, which can alter the chemistry of the air and leave misleading traces in both trees and ice. To tell the difference, scientists look for patterns across multiple records from different places on Earth. If a spike in carbon 14 appears in tree rings from Japan, Europe, and North America in the exact same year, and if ice cores from both poles show matching beryllium-10 increases, it becomes far more likely that the cause was global in scale, something like a huge solar storm, rather than a local volcanic blast. Even with these tools, the record we have is far from complete. Trees can only tell us about the years they lived through, and the oldest living trees stretch back only a few thousand years. Fossilized wood can extend that timeline, but it is rare and not always preserved well enough to yield accurate chemical data. Ice cores, too, are limited by how far back they can go before the layers become compressed or mixed by the slow flow of the glacier. Beyond a certain point, the signals blur and individual years cannot be clearly separated. There is also the problem that not every solar event leaves a strong, clear chemical mark. The strength of the signal depends on the direction and intensity of the particles that hit Earth. A storm that was immense but happened to miss our planet by a small margin might leave almost no trace at all in the geological record. Likewise, a storm that did strike us, but during a time when global climate conditions were shifting, could have its chemical signature hidden or altered by other atmospheric changes. This means that what we have uncovered so far may be only a fraction of the sun's most extreme moments. For every event we can point to with certainty, there could be others, perhaps even larger, that remain buried in the noise of the planet's history. Future techniques, using more sensitive detectors or analyzing new materials like cave deposits and deep-sea sediments, may reveal a richer and more frightening picture of just how often the sun has unleashed its fury on Earth. Each new discovery adds another piece to a puzzle that is still far from complete, reminding us that the true history of solar storms may be far older and far more dramatic than we have yet imagined. In July of the year 2012, a massive storm erupted from the surface of the Sunday. It began with a bright, blinding flare in the ultraviolet and X-ray spectrum, captured in extraordinary detail by NASA's Solar Dynamics Observatory. In those moments, the sun's surface seemed to twist and boil like a living thing, releasing an enormous coronal mass ejection, a vast bubble of superheated plasma and magnetic energy, millions of kilometers across, flung outward into space at speeds exceeding 1,000,000 miles per hour. The force behind it was staggering, the kind of power that could strip atmospheres from planets if conditions were right. From the observatory's vantage point, scientists watched the event unfold frame by frame, each new image revealing the expanding cloud of solar material surging outward. What they knew almost immediately was that this was no ordinary eruption. The ejected plasma was moving with incredible speed, and its magnetic field carried the dangerous potential to interact violently with Earth's own. A direct hit from such a storm could unleash the most destructive geomagnetic event in modern history. As the data poured in, calculations began. Using spacecraft positioned to monitor the sun from different angles, such as NASA's stereo satellites, scientists traced the path of the ejected material through the solar system. The grim truth became clear. the storm's trajectory had missed Earth's orbit by only a matter of days. Had our planet been slightly further along in its path around the sun, the cloud of charged particles would have slammed directly into our magnetic field. The consequences of such an impact were not hard to imagine, because experts had been studying scenarios like this for years. Power grids around the globe could have been knocked offline within minutes, as geomagnetically induced currents surged through transmission lines, overloading transformers and burning them out. Satellites could have been crippled or destroyed, leaving GPS navigation, telecommunications, and weather forecasting systems in chaos. Commercial air travel might have been forced to a halt as high-altitude radiation levels spiked, while spacecraft crews in orbit would have been at serious risk of exposure to dangerous radiation doses. The economic cost of such a disaster was estimated in the trillions, with some studies suggesting it could take a decade or more to fully rebuild and replace the damaged infrastructure. It would not be like a hurricane or an earthquake, where the destruction is limited to one region. This kind of storm would have been global in its effects, hitting every continent, every country, and every economy at once. Even nations far from the equator, normally less affected by geomagnetic storms, could have experienced severe blackouts and communication failures. What makes the 2012 event especially haunting is how close it came without most of the world even knowing. While scientists and space agencies tracked the storm's path with tense focus, the general public went about their daily lives unaware that an invisible bullet had just missed our planet. There were no headlines screaming about the danger, no emergency broadcasts. The sun had simply hurled one of its most powerful weapons into space, and by sheer luck, we were not standing in its path. The data from that near miss became a wake-up call for many in the scientific community. It showed in concrete terms that such events are not theoretical relics of history like the Carrington Event. They are ongoing threats in our cosmic neighborhood, capable of striking at any time. The 2012 superstorm remains one of the most powerful eruptions ever recorded in the modern era, and the fact that it missed Earth by only days is a reminder that the next one might not. From that moment onward, the push to better monitor, predict, and prepare for extreme space weather gained a new urgency, because the sun does not warn us before it decides to act. A superflare begins deep within the tangled magnetic fields of a star. The sun, like other stars, is not a smooth, quiet ball of light. Its surface is a restless sea of hot plasma, constantly moving and twisting under the influence of powerful magnetic forces. These magnetic fields can become knotted and stressed as the plasma churns. When the tension becomes too great, the fields can snap and reconnect in a process known as magnetic reconnection. This sudden rearrangement of magnetic lines releases enormous amounts of energy in an instant, far more than in a typical solar flare. On our sun, ordinary flares can already be astonishingly powerful, releasing the energy equivalent of millions of hydrogen bombs in just minutes. A superflare takes this to another scale entirely. In these rare events, the energy unleashed can be hundreds or even thousands of times greater than the most powerful flare our sun has ever produced in recorded history. The heat, light, and charged particles from such an eruption would expand outward through space, and if aimed at Earth, the consequences would be unlike anything modern civilization has faced. To study the potential for such extremes, astronomers look to other stars, particularly young and active ones. Using telescopes like NASA's Kepler Space Observatory, scientists have detected superflares occurring on stars similar to our Sunday. These younger stars often rotate faster, which drives more intense magnetic activity. Their surfaces are peppered with vast star spots, far larger than the sunspots we see on our star. These dark patches mark regions of intense magnetic fields, and when those fields collapse and reconnect, the resulting flare can be staggeringly bright, sometimes visible across hundreds of light years. By examining these stellar outbursts, researchers have gained clues about the conditions needed for superflares. A key factor seems to be the size and complexity of the magnetic structures on the star's surface. The larger and more twisted these structures become, the more energy they can store, and the more violent the release when they snap. Observations have shown that even stars that are not extremely young can produce superflares under the right conditions. This raises the question that is impossible to ignore. Could our sun still be capable of one? The answer is not entirely comforting. While our sun is older and rotates more slowly than many of the stars that produce superflares frequently, it still has the same fundamental magnetic processes. Theoretical models suggest that under rare and extreme conditions, the sun could store enough magnetic energy to unleash a superflare. Such an event might be triggered by an unusually large and complex sunspot region or by a buildup of magnetic stress over years. Evidence from Earth's own past hints that the sun has, at times, been more active than we might expect. Carbon-14 and beryllium-10 spikes in ancient tree rings and ice cores suggest bursts of radiation much stronger than anything in the modern era. While these events were not on the scale of the largest stellar superflares observed elsewhere, they prove that the sun is capable of producing far more powerful outbursts than what we are used to. If a true superflare erupted from our sun today, it would not just be a matter of dazzling lights in the sky. The electromagnetic pulse could disrupt satellites, destroy sections of the power grid, and flood the upper atmosphere with charged particles. Understanding how and why these immense bursts occur is not only a matter of scientific curiosity, but a necessity for preparing our technology-dependent world for what the sun might one day unleash. And the clues to that future lie in the distant but watchful eyes of other stars that remind us just how fierce and unpredictable stellar energy can be. Deep in the frozen layers of Earth's polar ice lies a record far older than any written history. Each winter, snowfall compresses into a thin sheet of ice, trapping within it tiny samples of the atmosphere and particles from space. Over tens of thousands of years, these layers stack up like the pages of an ancient diary, preserving evidence of events that no human ever saw. It was within these ice cores, drilled from Antarctica and Greenland, that scientists found something astonishing, a sudden and dramatic spike in certain isotopes like beryllium-10 and carbon-14, dating back thousands of years. These isotopes form when high-energy radiation from space collides with molecules in the upper atmosphere, breaking them apart and creating new atomic forms. The size of the spike told scientists that whatever had happened was far beyond the intensity of even the Carrington Event of 1859, the most famous solar storm in modern history. The first question was obvious. What could have caused such a surge in radiation? The smooth patterns of isotope levels before and after the spike suggested that this was not a slow buildup of cosmic rays from deep space, but a sudden, violent burst. When researchers ran simulations to match the data, they found that only an extreme solar event, possibly a prehistoric superflare, could explain radiation levels so high. Unlike ordinary storms from the sun, this one must have been hundreds of times more powerful, bathing the planet in a torrent of charged particles and electromagnetic energy. For humans alive at the time, small groups of hunter-gatherers scattered across the continents, the skies would have told a strange story. At night, auroras could have flared far closer to the equator than usual, shimmering in deep reds, greens, and purples. The air itself might have carried a faint metallic tang from ionization high above. Even without knowing the cause, they would have sensed something extraordinary and possibly dangerous unfolding over their heads. The environmental impacts of such a massive event would have gone far beyond the beauty of the sky. When high energy particles slam into the atmosphere, they can strip away ozone, the thin protective layer that shields life from the sun's harmful ultraviolet radiation. If the ozone layer thinned significantly after this prehistoric burst, the following months or years could have been marked by harsher sunlight, higher UV levels, and stress on ecosystems. Plants exposed to intense radiation may have suffered reduced growth, and some animals could have faced increased genetic damage from DNA mutations. Even small changes in the food web can ripple outward, affecting entire habitats. For early humans, survival during such a time would have meant relying even more heavily on shelter, clothing, and mobility to avoid the harshest conditions. Prolonged exposure to increased UV radiation could cause burns, eye damage, and a higher risk of disease. Without any understanding of atmospheric chemistry, they might have attributed these changes to angered spirits or displeased gods, embedding the event into myths that would echo through generations. The ice cores do not tell us exactly how long the radiation surge lasted, nor whether it came from a single colossal outburst or a cluster of powerful storms. What they do reveal is that our planet has faced space weather events far greater than anything in recorded history, and that life endured them. As researchers continue to drill deeper into the ice, they may find more of these ancient spikes, each one a silent warning that the sun's power is not bound by human timelines, and that even in the deep past, our world has been touched by forces vast enough to change its course. The sun, though it appears steady and unchanging in our daily sky, is anything but constant. Its surface roils with immense forces, shifting magnetic fields, and colossal streams of plasma that follow rhythms far larger than a human lifetime. One of its most important rhythms is the roughly 11-year solar cycle, a pattern in which the sun's activity rises and falls like a slow cosmic heartbeat. During the peak of this cycle, known as the solar maximum, the sun becomes a restless giant, its surface peppered with dark sunspots and its atmosphere crackling with powerful flares and coronal mass ejections. At the opposite phase, the solar minimum, sunspots can vanish entirely for weeks or months, and the sun appears calmer. But calm on the surface does not mean harmless. Sunspots are more than just dark patches. They are windows into areas of intense magnetic activity, where twisted magnetic field lines can snap and release vast amounts of energy in an instant. The more sunspots that appear, the higher the probability that one of these regions will unleash a flare or a storm. That is why solar maximum is a time of heightened vigilance for space weather forecasters, since each eruption has the potential to send a wave of charged particles toward Earth. However, the sun is full of surprises. Even during periods of low sunspot activity, when the solar cycle is in its quiet phase, it can still produce sudden and violent outbursts. In fact, some of the most puzzling events in solar history have happened during what should have been lulls in activity. This unpredictability makes forecasting a challenge. It is as if the sun sometimes ignores its own schedule, producing massive eruptions when the magnetic landscape is supposedly stable. These rare but powerful bursts remind us that the 11-year cycle is more of a general guideline than a strict rule. Scientists track the solar cycle by counting sunspots and measuring the sun's magnetic polarity, which actually flips with each cycle. Over decades of observation, They have learned that while the cycle itself is reliable in its broad strokes, the intensity of each maximum can vary greatly. Some peaks are mild, with relatively few storms, while others unleash a flurry of activity capable of disrupting satellites, power grids, and radio communications on Earth. Understanding why one cycle is more active than another remains an open question, and that uncertainty leaves room for risk. The sun's magnetic fields are the driving force behind this cycle. Deep within its core, charged particles move in swirling currents, creating a magnetic dynamo. Over years, these magnetic fields become tangled and rise to the surface, forming sunspots. Eventually, the fields reorganize, reversing the sun's magnetic poles and beginning a new cycle. This magnetic dance is far more complex than any simple clockwork, which is why sudden eruptions can still emerge even when the visible signs of activity are scarce. Modern technology has given scientists tools to study the sun in detail never before possible. Spacecraft like NASA's Solar Dynamics Observatory watch for changes in the solar atmosphere, while ground-based observatories record sunspot patterns and flare activity. Yet even with all this data, predicting the exact moment of a major eruption remains out of reach. The sun may give subtle hints a growing sunspot, a sudden brightening in ultraviolet light, but it can still erupt without warning. This element of unpredictability is what makes solar storms such a persistent concern, because our world is now so tightly bound to the flow of electricity and satellite signals that even one unexpected outburst could ripple through daily life in ways we are only beginning to fully grasp. Imagine a morning that begins like any other. The sun has been restless for days, but most people on Earth are unaware of the storm building 93 million miles away. Then, without warning, a coronal mass ejection bursts from the sun's surface, hurling billions of tons of charged particles into space at millions of miles per hour. This wave of solar plasma, invisible to the naked eye, races outward in all directions. In this imagined moment, its path happens to align perfectly with Earth's orbit, and it is only a matter of hours before impact. The first sign comes not from the ground, but from satellites stationed between Earth and the Sunday instruments detect an intense spike in solar wind speed, density, and magnetic orientation. Space weather forecasters know that if the incoming magnetic field aligns in a certain way, pointing opposite to Earth's own magnetic field, the two will connect and allow an enormous amount of energy to flood into the planet's magnetosphere. There is no way to deflect it. The only thing left is to brace for impact. When the wave finally arrives, the magnetosphere is compressed like a balloon being squeezed, pushing the boundary that normally shields us from solar particles closer to Earth. High above the atmosphere, satellites are the first to feel the effects. Their sensitive electronics are bombarded by energetic protons and electrons, which can overload circuits, flip bits in memory systems, and, in many cases, destroy them outright. Navigation satellites begin to fail. Weather satellites go dark. Communications relays flicker and die, one after another. The chain reaction has begun. At the same time, massive currents are induced in Earth's upper atmosphere. These currents spill down into the surface, finding their way into the planet's vast web of electrical infrastructure. Power lines stretch for hundreds of miles, acting like giant antennas that collect and channel the surge directly into transformers and substations. Within moments, transformers overheat, insulation burns away, and steel cores warp from the intense energy. Regions begin to lose power. What starts as scattered blackouts spreads rapidly as more components fail under the strain. Without electricity, pumping stations stop moving water into cities. Fuel distribution grinds to a halt as gas stations lose their power to operate pumps. Refrigerated goods begin to warm in warehouses and supermarkets. Emergency services try to respond, but their radio systems are jammed by the electromagnetic storm, leaving them blind and isolated. Commercial airliners are forced to land, unable to navigate without GPS or reliable communication. Within days, the deeper consequences take hold. Financial systems, dependent on global computer networks, are unable to process transactions. The internet is fragmented as critical nodes remain offline. Cargo ships remain anchored at ports, waiting for instructions that never come. In warehouses, goods pile up as logistics systems fail. The modern supply chain, fine-tuned to operate on just-in-time deliveries, begins to collapse. Meanwhile, above the chaos, the night sky is transformed. Auroras ripple far beyond the poles, shimmering green, red, and violet even above tropical skies. For ancient peoples, these lights might have been seen as omens, but today they are a sign of a magnetic system pushed to its limits. The same beauty in the heavens is paired with silent devastation on the ground, as the world struggles to function without the invisible lifelines it has come to depend upon so completely. Modern life runs on an invisible current. Every screen that lights up, every voice that travels through the air, every shipment that arrives on time is part of a vast, delicate system powered by electricity and guided by satellites orbiting far above. Most of us never think about how deeply our daily survival depends on these unseen networks until they are threatened. But the truth is that our civilization is not built to endure without them for long. The dependency begins with electricity itself. Without it, the devices we use to work, communicate, and store information simply go dark. But it is more than convenience at stake. Electricity powers the pumps that draw clean water into our homes. It keeps food chilled in massive refrigerated warehouses. It drives the conveyor belts that move goods through factories and shipping centers. Even the most basic needs, light to see, heat to keep warm, air conditioning to keep cool, are only possible because of an unbroken flow of energy from power stations through transformers and lines to our walls. High above Earth, satellites play their own silent but vital role. Global Positioning System satellites are not just for mapping directions in a car. Their timing signals are the heartbeat of financial transactions, energy grid coordination, and even the synchronization of internet servers. Communication satellites carry television signals, international phone calls, and data relays for remote regions. Weather satellites feed meteorologists the information they need to warn communities about storms. Remove them from the picture, and many of the systems we rely on would not just slow down, they would collapse. Hospitals are among the most vulnerable in such a scenario. While they have backup generators, these are designed to run for hours or days, not weeks. Life support machines, surgical equipment, refrigeration for medicines, and the complex computer systems that track patient care all depend on stable power and communication networks. Without them, even the most skilled doctors and nurses would face impossible odds in saving lives. Food storage is another critical point of weakness. Modern cities do not keep large reserves of food on hand. Supermarkets and restaurants rely on constant deliveries from distribution centers, which in turn depend on cold storage facilities to keep perishable goods safe. If refrigeration fails, entire stockpiles of meat, dairy, and produce can spoil in a matter of days. That is not just an economic loss, it is a blow to food security. Transport links the entire chain together. Trucks, trains, cargo ships, and airplanes are all coordinated through digital systems. Even a simple truck delivery is tied to GPS tracking, digital scheduling, and payment processing. If these systems fail, goods cannot move efficiently, and bottlenecks form within days. What begins as a delay in one area can ripple outward into shortages and economic disruption across entire regions. In cities, the impact is magnified by population density. Millions of people live within areas where nearly all resources are brought in from outside. A disruption in power or supply chains can quickly turn into a crisis, as there is little local production to fall back on. In rural areas, the situation can be different. Some communities may have their own water wells, off-grid power systems, or local food sources, giving them a degree of resilience. But even rural life is now tied to broader systems, and isolation can make recovery slower when outside help is needed. The fragility of our modern civilization lies in this interconnection. Every link in the chain depends on every other, and the higher our technology climbs, the more we rely on systems that cannot be repaired easily if they break all at once. Radiation from the sun is always present, streaming toward Earth in a steady flow of charged particles. Most of the time, our planet's magnetic field and thick atmosphere shield life from the worst of it. But during an extreme solar storm or superflare, that shield can be pushed to its limits. The results would not only threaten our technology, but could reach deep into the biological systems that sustain life. The human body is built to handle small doses of natural background radiation, but astronauts working beyond the protection of Earth's atmosphere and magnetic field live with a far more fragile defense. On the International Space Station, they already receive higher radiation exposure than people on the ground. A strong solar storm can send those levels spiking to dangerous highs in a matter of hours. Without immediate shelter inside specially shielded sections of the station, astronauts risk acute radiation sickness. Symptoms can begin with nausea, fatigue, and skin burns, but in higher doses, the damage can reach bone marrow, vital organs, and DNA itself. For missions beyond low Earth orbit, such as planned journeys to the Moon or Mars, the danger becomes even greater, as there would be no quick return to Earth and no thick planetary magnetic shield to hide behind. Even those of us who never leave the ground are not completely safe if we happen to be flying during a major solar event. Commercial aircraft cruise at altitudes where the atmosphere is thinner, which means there is less natural shielding. Pilots, flight attendants, and frequent flyers already accumulate more cosmic radiation exposure over time compared to people who stay on the ground. During a powerful solar storm, radiation levels at flight altitudes can temporarily rise to levels many times higher than normal. This could be especially risky for long-haul flights over polar routes, where Earth's magnetic field lines funnel charged particles downward. Airlines monitor solar weather and can reroute flights in extreme cases, but sudden events can leave little time to act, especially if communication systems are also disrupted. Radiation from an extreme solar event can also affect the natural environment in less visible but equally profound ways. One of the greatest concerns is ozone depletion. High-energy particles from the sun can break apart molecules in the upper atmosphere, triggering chemical reactions that reduce ozone levels. The ozone layer is Earth's protective filter, absorbing much of the sun's harmful ultraviolet radiation before it reaches the surface. A thinning ozone shield would allow more UV light to bathe the planet, increasing risks of skin cancer and cataracts in humans, but also harming plants, plankton, and countless other organisms that form the foundation of food chains. Wildlife, too, could be affected in ways we do not fully understand. Migratory birds, sea turtles, and even some insects use Earth's magnetic field to navigate. A massive solar storm can disturb that field, confusing these animals and disrupting breeding or feeding patterns. Marine life near the surface could be exposed to higher UV levels if ozone depletion occurs, affecting everything from tiny phytoplankton to larger fish that rely on them for food. The chain of impacts from such radiation is complex. It begins with invisible particles traveling through space at near light speeds and ends with changes in health, ecosystems, and atmospheric chemistry here on Earth. Throughout history, the sun has been more than just the provider of light and warmth. It has been a powerful driver of Earth's climate, shaping weather patterns, influencing harvests, and even playing a role in the rise and fall of civilizations. Scientists have traced periods of unusual climate behavior to changes in solar activity, where the sun's output varies over years, decades, and even centuries. These variations are often subtle compared to the dramatic flare of a single solar storm, yet over time, they can steer the planet's climate in surprising directions. One of the most famous examples comes from the period known as the Maunder Minimum, which lasted from the mid-17th to the early 18th century. During this time, sunspot numbers dropped sharply for several decades. Historical records show winters across Europe and North America became far harsher, rivers froze for longer periods, and growing seasons shortened. This coincided with part of what scientists call the Little Ice Age, a time of cooler temperatures that disrupted agriculture, caused crop failures, and triggered food shortages. While volcanic eruptions and natural ocean cycles also played a role, the prolonged quiet in solar activity appears to have been a major factor. The link between solar variability and climate becomes even clearer when looking at other unusual events in the past. Ice core samples from Greenland and Antarctica preserve chemical signatures that align with both solar cycles and periods of climate shift. These records suggest that the sun's changing energy output, even in small percentages, can ripple through the Earth's atmospheric systems. The process is complex, involving changes in ultraviolet radiation that alter the chemistry of the upper atmosphere, which in turn affects wind patterns and ocean currents far below. When it comes to massive solar flares or superflares, the question becomes whether such an event could cause rapid, noticeable changes in our weather. A flare itself primarily sends radiation and energetic particles, which have more immediate impacts on technology and atmospheric chemistry than on temperature. However, if the flare is large enough to cause significant ozone depletion or inject huge amounts of charged particles into the atmosphere, there could be short-term effects on climate. For instance, altered jet stream patterns or changes in high-altitude clouds could temporarily shift storm tracks, rainfall, and wind patterns over wide regions. In the long term, repeated strong solar events might amplify these effects. If the sun entered a period of unusually high flare activity, with multiple intense events in a short span of time, the combined atmospheric changes could influence seasonal weather and even multi-year climate patterns. This would be especially true if the increased radiation altered the balance of greenhouse gases like ozone, methane, and water vapor in the stratosphere, as each of these plays a role in trapping or reflecting heat. While human-driven climate change now dominates the global conversation, the sun remains a powerful background force that can add layers of complexity to our planet's climate system. Historical records, tree rings, and ice cores tell us that when the sun's mood shifts, Earth responds. Understanding these connections is vital because a massive flare in the modern era would not only test our technology, but might also subtly or abruptly alter the rhythms of the planet's weather. And as the sun continues its cycles, the possibility of such interactions remains very real, blending the science of space weather with the intricate story of Earth's climate. If you could see Earth through the eyes of a solar storm, the planet would not look like a simple blue marble. It would appear as a patchwork of magnetic zones, each with its own strengths and weaknesses against the sun's fury. Some areas are like fortresses, shielded by geography and infrastructure design, while others are like open doors, where the right kind of solar blast could send shock waves through every cable, transformer, and satellite connection. The first thing to understand is that vulnerability is not spread evenly across the globe. The regions most at risk are generally closer to the poles because the Earth's magnetic field lines bend downward there, creating wide open funnels for charged particles to enter the atmosphere. Northern countries like Canada, Norway, Sweden, and Finland sit right beneath these magnetic gateways. When a coronal mass ejection, or CME, collides with Earth, the energetic particles follow the magnetic field lines straight into these high-latitude regions. The result is not only the dancing glow of the aurora, but also intense electrical currents induced in the ground and power grids. Canada's vulnerability, for example, is made worse by its geology. Much of the Canadian Shield is made of ancient, non-conductive rock, which forces the storm-induced electrical currents to flow through man-made systems instead of dissipating harmlessly into the ground. In a strong solar storm, this means transformers and transmission lines can be overwhelmed in minutes. In fact, a geomagnetic storm in March of 1989 knocked out Quebec's entire power grid in just 90 seconds. On the other side of the world, Northern Europe shares similar risks. The dense network of interconnected power systems makes the region efficient in normal conditions, but more fragile when a massive surge sweeps through. Iceland, Greenland, and parts of Russia also sit in zones where geomagnetic disturbances can be far stronger than at lower latitudes. By contrast, equatorial regions experience weaker direct geomagnetic impacts because the field lines are more horizontal there, deflecting much of the charged particle flow. However, this does not mean they are completely safe. Lower latitude countries can still suffer serious damage if their infrastructure is heavily interconnected with higher latitude grids. For example, in the United States, while southern states are less exposed to the full strength of geomagnetic currents, they remain vulnerable because the national grid ties them to northern states where the storm's effects are stronger. Air travel routes also follow a similar risk map. Flights that pass over polar regions, such as those connecting North America and Asia through the Arctic, are more susceptible to communications, blackouts, and increased radiation exposure during strong solar storms. Airlines sometimes reroute these flights during heightened solar activity, adding hours to travel time and significant cost. Satellite systems face a more global form of vulnerability. High-energy particles can reach satellites in all orbital paths, but certain orbits, especially polar and geosynchronous ones, are more exposed to prolonged bombardment. Damage here ripples worldwide, affecting navigation, weather forecasting, and global communications, no matter where the satellite's users are located. The pattern is clear. High latitudes face the greatest direct electrical risks, mid-latitudes carry interconnected exposure and equatorial zones, while safer from geomagnetically induced currents remain deeply tied to the consequences through shared technology and supply chains. This invisible vulnerability map is as much about magnetic physics as it is about the way humanity has wired itself together. And as the sun's activity builds toward its peaks, these magnetic gateways and the networks connected to them will determine who feels the first and hardest shocks when the next great storm arrives. When we think about the risks of a massive solar storm, Our minds often jump to blackouts, dead satellites, and communication failures. But there is another layer of vulnerability that is far more unsettling. Modern defense systems, both on the ground and in space, rely heavily on the constant flow of data between satellites, radars, and command centers. If that flow is disrupted or distorted by an intense burst of solar activity, the consequences can go beyond technological inconvenience. They can escalate into political crises and even military miscalculations. In most countries, national security depends on a web of early warning systems that watch for potential threats. Ground-based radars scan the skies for incoming aircraft or missiles. Satellites monitor everything from troop movements to missile launches. Naval fleets depend on GPS positioning to coordinate maneuvers, and air defense relies on precise communications to respond to emergencies. All of these systems depend on electronics that are sensitive to electromagnetic interference. A strong coronal mass ejection slamming into Earth can send streams of charged particles into the upper atmosphere, where they disturb radio signals and scramble radar returns. Imagine a situation in which a military radar suddenly goes blind in the middle of heightened global tensions. A satellite link carrying intelligence data between continents drops without warning. High-frequency radio channels used for secure communications turn to static. These are not science fiction scenarios. They are events that solar activity can trigger in minutes. For the people inside a defense command center, a sudden blackout in communications could be interpreted as hostile action, especially if they do not immediately know the cause. History has already given us glimpses of how dangerous this can be. During the Cold War, there were several occasions when solar storms caused malfunctions in early warning systems. In one case, a radar system in North America reported what appeared to be incoming missiles from the Soviet Union. Investigators later determined that the false reading was caused by ionospheric disturbances linked to solar activity. In another incident, a communications blackout between military outposts occurred during a period of heightened alert, raising fears of an intentional attack before scientists identified it as the result of a geomagnetic storm. The risk becomes even greater when you consider that nuclear arsenals are on constant watch. Launch detection systems use infrared sensors aboard satellites to look for the heat signatures of missile launches. These sensors can be blinded or produce false positives during intense solar storms when the sun's own activity floods them with radiation. If such an event occurred during a time of political tension, the decision makers on both sides might have only minutes to decide whether the alert was real. That narrow window leaves little room for careful analysis. Naval operations are also highly sensitive to these disruptions. Submarines that operate deep under the ocean surface rely on very low-frequency radio signals to receive orders, and these signals pass through the ionosphere, which becomes unstable during strong geomagnetic events. In such conditions, a fleet could be temporarily cut off from its command structure, unable to confirm orders or receive updated mission instructions. In space, military satellites themselves can be damaged or disabled by high-energy particles from a solar storm. Some may lose orientation, others could suffer onboard computer failures. In the chaos of losing multiple surveillance and communication platforms, both sides in a conflict might misinterpret the situation. A purely natural event could mimic the effects of a coordinated cyber attack or a deliberate strike on infrastructure. This is why military planners quietly pay close attention to space weather forecasts. They need to distinguish between an attack and a solar storm before making decisions that could alter the course of history. But forecasting solar events is not perfect, and even with preparation, The moments during a sudden blackout remain tense. When the sun flares at the wrong time, the danger is not only in the damage it causes, but also in the misunderstandings it can create in a world where seconds matter and mistrust runs deep. Over the centuries, oceans have been both a highway and a barrier, connecting civilizations while also testing their limits. Today, our ships cross them with pinpoint precision, guided by satellites that can place a vessel's location within a few meters. Aircraft streak across continents and seas on invisible pathways, their routes calculated by constantly updated navigation systems. But these modern achievements rest on a fragile foundation of technology that is vulnerable to the charged particles hurled at Earth during a major solar storm. When a coronal mass ejection collides with our planet's magnetic field, one of the first systems to feel the impact is GPS. These signals, transmitted from satellites orbiting more than 20,000 kilometers above Earth, are weak by the time they reach the surface. A burst of solar radiation can distort the ionosphere, the layer of charged particles that these signals pass through, causing them to scatter or fade. For a ship navigating narrow channels or an aircraft flying over open ocean without visible landmarks, even a small navigation error can be dangerous. A deviation of just a few kilometers could send a vessel off its safe course or take an aircraft away from its planned flight corridor. The disruption does not stop there. Beneath the oceans, an unseen network of fiber optic cables carries most of the world's internet traffic. These cables themselves are not directly damaged by solar radiation, but the repeaters and power supply systems that keep the signals moving are connected to the global electrical grid. Strong geomagnetically induced currents can surge into these systems, damaging them or shutting them down. In extreme cases, a single critical failure in the wrong location could sever a link between continents. The impact would ripple outward, not just slowing communications, but also affecting global financial systems, emergency services, and international coordination during a crisis. For aviation, the risks are layered. Communication with aircraft flying over the poles depends heavily on high-frequency radio, which bounces off the ionosphere to reach long distances. During strong solar storms, this layer can become so disturbed that radio waves are absorbed instead of reflected. In such conditions, pilots may suddenly find themselves unable to reach ground controllers. This is especially serious on transpolar routes, where there are no nearby diversion airports and satellite communications may also be degraded. Weather tracking is another critical link that can be compromised. Modern forecasting relies on satellites that monitor storm systems, ocean currents, and atmospheric patterns in near real time. These satellites provide early warnings for hurricanes, typhoons, and other severe weather events. A strong solar storm can damage their sensors, overload their electronics, or interfere with their data transmission. Without the steady stream of images and measurements they provide, meteorologists could be left partially blind to developing storms. That loss of visibility can mean less time to warn communities, ships, and aircraft in harm's way. The combination of navigation errors, communication blackouts, and loss of weather monitoring creates a dangerous environment where small problems can quickly escalate. A cargo ship missing its waypoint in heavy seas, an aircraft forced to change course without guidance, or a storm building unseen over the horizon. These scenarios are not the product of imagination, but the predictable consequences of space weather meeting our dependence on fragile systems. And just as the oceans connect nations, so too do the vulnerabilities that run through their depths and the skies above. History has a way of leaving quiet warnings for those who choose to listen. For humanity, some of the clearest warnings about the sun's power have come in the form of near misses, moments when our star reminded us of its strength but spared us the full consequences. These events are scattered across centuries, recorded in old newspapers, telegraph logs, power company reports, and now in the vast data archives of space agencies. Each one tells a story, not just of damage, but of how close we have come to something far worse. The first and most famous of these warnings came in September of 1859 during what would later be called the Carrington Event. On an otherwise ordinary day, British astronomer Richard Carrington was sketching sunspots when he saw an intense flash of white light burst from the sun's surface. Hours later, the skies across much of the world erupted in auroras so bright that people could read newspapers at night. Telegraph systems crackled with uncontrolled currents, operators received shocks, and some telegraph stations caught fire. The event happened in an age before electronics defined civilization, yet even then, the effects were disruptive enough to be remembered more than a century later. In May of 1921, the world had changed. Telegraph lines had multiplied, and electric railways were spreading through cities. That month, a massive solar storm hit Earth, sending geomagnetically induced currents racing through wires. Telegraph service was interrupted across the globe. In New York, parts of the rail system caught fire as the overload burned through control systems. This storm is now thought to have been nearly as strong as the Carrington Event, but it struck in a time when electricity was still a growing part of daily life. Even so, it left damage that would be far more costly in today's interconnected world. Fast forward to March of 1989, the province of Quebec was plunged into darkness when a solar storm overwhelmed its power grid in just 90 seconds. More than 6 million people lost electricity for hours, and the disruption extended into the northeastern United States. The storm was not even close to the strength of Carrington, yet it was enough to cause cascading failures across one of the most developed regions in the world. This was one of the first times modern society truly experienced the vulnerability of its infrastructure to space weather. Then came July of 2012, when the sun unleashed one of the most powerful coronal mass ejections ever recorded. It missed Earth by only 9 days. Had the timing been slightly different, it could have delivered a blow to global infrastructure on a scale far beyond anything in human history. NASA's Solar Dynamics Observatory and other satellites captured the event, giving scientists an unparalleled view of just how violent our star can be. Many researchers now regard this as the closest call humanity has had in the space age, a reminder that our survival in that moment came down to the smallest twist in the sun's rotation. These events are not evenly spaced or predictable, yet they show a pattern. Every few decades, the sun hurls something at us that could alter the course of our civilization. Sometimes we take a direct hit, sometimes the worst of it slides past, but statistically, the odds build with time. The sun does not remember its last strike, and it does not wait for us to be ready. As history shows, luck has been our silent ally, but luck is never a permanent shield, and the clock between these great storms is always ticking forward. High above Earth, far beyond the reach of weather balloons or ground-based instruments, a silent network of spacecraft keeps its gaze fixed on the Sunday. These sentinels belong to agencies like NASA, NOAA, and the European Space Agency, and their mission is not to study ordinary weather, but something far more unpredictable and dangerous space weather. Every image they send back, every stream of data they record, is part of a constant effort to watch for the first signs of trouble on our star's restless surface. NASA's fleet includes spacecraft like the Solar Dynamics Observatory, which captures high-resolution images of the sun in multiple wavelengths every few seconds. These images reveal shifting patterns of magnetism, growing sunspots, and the flashes of solar flares in real time. The Parker Solar Probe, launched in 2018, dives closer to the Sun than any spacecraft in history, sampling particles and magnetic fields in the corona, the very region where explosive eruptions begin. Each observation adds another piece to the puzzle of how and when these storms might form. NOAA's Space Weather Prediction Center plays a crucial role in turning that raw space data into actionable alerts. Using information from satellites such as the Deep Space Climate Observatory, or DSC-OVR, stationed a million miles away at the Lagrange Point 1, scientists monitor the solar wind before it reaches Earth. Here, DSC-OVR can detect a surge of charged particles, measure their speed and density, and send that information back to Earth in near real time. This early warning is one of our best defenses because it allows operators of power grids, satellites, and communication systems to take protective measures before the wave of energy arrives. The European Space Agency adds another layer of global coverage with missions like Solar Orbiter. Its instruments track the Sun from unique angles, allowing scientists to study regions that are difficult to observe from Earth's perspective. By combining ESA's data with NASA's and NOAA's, forecasters can piece together a more complete picture of the Sun's activity, much like meteorologists combining radar and satellite imagery to predict storms here on Earth. But unlike weather on our planet, which can often be forecast days in advance, space weather gives us far less time. A major solar flare can erupt with almost no warning, sending a blast of X-rays and ultraviolet radiation that reaches Earth in just over 8 minutes. A coronal mass ejection, or CME, can take anywhere from 15 hours to several days to arrive, depending on its speed. If we are lucky, satellites like DSCOVR will detect the incoming cloud of charged particles about 30 to 60 minutes before impact. That is enough time to issue alerts, but not nearly enough to avoid all consequences. One of the biggest challenges is that even when we see a CME erupt from the Sun, we cannot always know its exact direction or magnetic orientation until it is close to Earth. A CME aimed directly at our planet might still pass us by if its path curves slightly, while one that appears to be heading away can still hit if its structure is wide enough. The orientation of its magnetic field matters too. If it is aligned opposite to Earth's pair, it can open cracks in our planet's magnetic shield, allowing far more energy to pour in. Predicting this with precision is still beyond our reach. This means that every new instrument, every improvement in solar modeling, is part of a race against time. The Sun will keep firing off storms whether we are ready or not, and the difference between a minor disruption and a global-scale disaster may come down to how many minutes of warning we can gain before the first wave hits. The story of forecasting space weather is still unfolding, and each mission sent toward the Sun is a step toward understanding and surviving the next great storm. The first step in preparing for a future solar storm begins long before the first flare erupts on the Sunday around the world. Engineers and scientists are working to make our most critical infrastructure more resilient. Power grids, which are among the most vulnerable systems during a geomagnetic storm, can be hardened through the installation of protective devices that block or redirect dangerous electrical surges. Some countries are investing in transformer designs that can better withstand sudden overloads, as these massive pieces of equipment are both costly and slow to replace. Even simple measures, like creating the ability to temporarily disconnect parts of the grid, can prevent a chain reaction of blackouts that would otherwise spread across entire regions. In space, satellites face their own challenges. Without protection, a burst of energetic particles from the sun can fry sensitive electronics and permanently disable them. To counter this, satellite manufacturers are adding radiation shielding to critical components and designing systems that can be powered down during a predicted storm. Some satellites are equipped with redundant systems so that if one fails, another can take over without losing vital services like GPS, weather monitoring, or communication. These precautions are expensive, but the cost of losing even a single key satellite in orbit could be far higher in terms of global disruption. Governments are also recognizing that preparing for a major solar storm requires more than just physical upgrades. Many are building protocols for rapid response when space weather warnings are issued. Control centers for power grids, airlines, shipping companies, and emergency services receive these alerts and follow procedures designed to minimize damage. This might mean rerouting flights away from polar routes where radiation is higher, or putting certain satellites into safe mode until the threat passes. The more quickly and efficiently these measures can be carried out, the greater the chances of avoiding catastrophic loss. On a smaller scale, communities and individuals also have a role to play. Just as people prepare for hurricanes or earthquakes, they can prepare for the possibility of a days-long or even weeks-long blackout caused by a severe geomagnetic storm. Storing non-perishable food, clean drinking water, and basic medical supplies can be the difference between discomfort and real danger. Having alternative sources of light and heat, such as candles, solar-powered lamps, or wood stoves, can help families manage without electricity. Battery-powered or hand-crank radios remain valuable tools for receiving news and emergency updates when modern communication systems are down. For those who rely on medical devices or refrigerated medication, personal preparedness is even more critical. Backup generators, portable battery packs, or arrangements to temporarily relocate to a powered facility could be life-saving. Communities can establish local support networks so that vulnerable residents, such as the elderly or those with mobility challenges, are not left isolated if transport and communication are cut off. The most effective preparation combines all of these levels of action. A resilient society depends on strong infrastructure, coordinated emergency planning, and individual readiness. Just as important is public awareness. Understanding the risk of a solar superstorm and knowing the steps to take before it happens ensures that when the next big one comes, fewer people will be caught by surprise. While no amount of preparation can make us completely immune to the sun's power, every measure taken now increases the odds that we can endure its next outburst without sliding into chaos. And as technology continues to advance, these preparations will evolve, shaped by the lessons learned from both past storms and near misses, carrying us forward toward the future. When we look deep into the Earth's natural records, we find stories that were written long before humans could read them. Layers of ice from Greenland and Antarctica hold trapped bubbles of ancient air, carrying chemical fingerprints of events that shook the planet thousands of years ago. Tree rings show scars from seasons when growth faltered, hinting at unusual shifts in sunlight or temperature. Even the ocean floor preserves traces of cosmic particles that rain down during violent episodes in the sun's history. These silent witnesses remind us that the forces capable of disrupting our lives today have struck the Earth before, sometimes with an intensity we can barely imagine. Ancient evidence matters because it shows the true range of the sun's behavior over long stretches of time, far beyond the brief window of human technological history. Modern scientists have been directly monitoring solar activity for just over a century, Yet the sun has been cycling through bursts of energy for billions of years. Without looking to the past, we might think the storms we have seen in recent decades are as bad as it gets. Ice cores and other natural archives prove otherwise. Some recorded events make the famous Carrington storm of the 19th century look modest, suggesting that our modern systems have never been tested by the sun's full power. One of the most dangerous attitudes is the belief that a rare event in the distant past will not repeat in our lifetime. This way of thinking has misled civilizations before. In ancient times, rivers that had flooded once in living memory were often treated as forever tamed, leading people to build in floodplains that were eventually reclaimed by the water. Volcanic slopes became farmland after centuries of quiet, only to be swept away by an eruption. The same mistake can be made with solar storms. The quiet decades we have experienced can foster a false sense of security, especially when the threat is invisible until it strikes. History reshapes our understanding of risk because it forces us to confront uncomfortable truths. In the 21st century, most of our knowledge about space weather comes from the short period in which humans have had electricity, satellites, and global communication. But these are the very systems that stand to suffer the most when the sun unleashes a powerful outburst. If an ancient solar event far stronger than anything in recorded history were to occur today, its consequences would be multiplied by our dependence on fragile technology. The past also teaches us how interconnected natural systems can be. Some ancient solar storms may have influenced weather patterns, disrupted animal migrations, or altered atmospheric chemistry for years. Understanding these links helps scientists build more accurate models of how a similar event might play out now. Historical patterns also reveal that the sun's most extreme outbursts do not follow a predictable timetable. They can arrive during periods of high solar activity or surprise us during quieter phases, making it impossible to rely on a single warning sign. By piecing together these lessons, scientists gain a clearer picture of the true risks we face. The ancient record is not simply a curiosity for historians or geologists. It is a guidebook written in ice, stone, and sediment, showing us what the sun is capable of and what the earth has endured. The stories hidden in those records are not distant myths. They are warnings, urging us to prepare for a future that could mirror the past in ways we are only beginning to grasp. And as research continues, each new finding has the potential to change how we measure danger, plan our defenses, and imagine our survival in the face of the sun's next great test. Every sunrise is a reminder of the sun's generosity. Its light pours across the horizon, spilling warmth into cold air, painting the sky in colors that have inspired humans for tens of thousands of years. Without it, Earth would be a frozen, lifeless rock drifting in space. The sun's energy feeds every plant, stirs every wind, and drives the water cycle that shapes the land. It fuels the photosynthesis that produces oxygen for our lungs and food for our tables. Even the fossil fuels we burn are ancient sunlight, stored in plants and plankton that lived millions of years ago. Yet the same star that sustains all life has the power to threaten it. The sun is not a calm lantern in the sky, but a restless sphere of nuclear fire, constantly churning with magnetic storms. Most of the time, its outbursts are gentle, creating the auroras that dance at Earth's poles. But every so often, it releases far more than beauty. It hurls charged particles into space, sometimes with enough force to disrupt satellites, overload power grids, and strip away parts of the atmosphere itself. This paradox is part of what makes the sun both fascinating and dangerous. We cannot live without it, yet we are always at its mercy. The balance between the sun as creator and the sun as destroyer is delicate, and it plays out on scales both vast and personal. In our daily lives, we rely on the sun for warmth and light. On a planetary scale, we depend on its stability to keep climates within ranges that human civilization can endure. A slight increase or decrease in the sun's energy output over time could shift weather patterns, alter ocean currents, and change the growing seasons that have fed societies for millennia. Our dependence runs deeper than most people ever think about. The electricity that powers our cities, the GPS that guides ships and planes, the satellites that carry television signals and weather forecasts, all depend on a relatively calm Sunday. A single, severe solar storm could knock out some of these systems for days, weeks, or longer. Without modern navigation, airplanes could be grounded. Without functioning satellites, global communications could fracture. Even food and medicine supplies could be disrupted if transport and refrigeration systems failed. The sun does not have to scorch the earth to endanger us. It only has to disrupt the delicate web of technology that we have woven around ourselves. Life on Earth has always walked this line between reliance and risk. In the deep past, before humans, solar activity may have played a role in both the flourishing and the decline of certain species. Plants and animals evolved under the rhythms of day and night, as well as the longer cycles of solar variation. Some of those rhythms have been steady enough for life to adapt. Others have come as sudden jolts, forcing quick and sometimes brutal changes. It is this fine line that makes the sun's dual nature so important to understand. We live in the comfort of its warmth, yet the same forces that sustain us are capable of transforming our world in ways we might not be ready for. Just as the sun rises and sets each day, our relationship with it carries both the promise of life and the shadow of catastrophe. And as we continue to study its patterns, we are reminded that the story of the sun is also the story of our own survival. The sun may feel like an old friend, steady and dependable, but in truth it is a restless and powerful force. Every living thing on Earth owes its existence to its warmth and light, yet the same energy that nurtures life could, in extreme circumstances, threaten to erase it entirely. To understand whether that is truly possible, we have to look closely at the protections that stand between us and the sun's raw power and the limits of those protections. Earth's atmosphere is our first great shield. It blocks the most dangerous ultraviolet and high-energy radiation from reaching the ground, absorbing much of it in layers like the ozone. Without this filter, unprotected skin would burn in minutes, and DNA and cells would be damaged beyond repair. Above the atmosphere, our planet's magnetic field forms another defense, stretching out into space in a vast bubble known as the magnetosphere. It deflects charged particles that stream from the sun, steering them harmlessly toward the poles, where they create auroras instead of striking the surface. Together, these two systems have allowed life to thrive for billions of years. Yet no shield is invincible. The atmosphere can be eroded, slowly or suddenly, if the assault is intense enough. Scientists studying planets like Mars have found that it once had a thick atmosphere and possibly flowing water, yet it lost both. The leading explanation is that Mars's magnetic field faded long ago, leaving its air vulnerable to being stripped away by the solar wind. Over millions of years, this transformed it from a place that might have supported life into the cold, dry desert we see today. While Earth's magnetic field is far stronger and more stable, it too can be weakened or reshaped during periods of extreme solar activity. Worst-case models consider events far more powerful than anything in recorded human history. A massive solar flare, paired with a coronal mass ejection of unprecedented strength, could theoretically compress the magnetosphere so much that charged particles penetrate deep into the atmosphere. In extreme scenarios, this could destroy large portions of the ozone layer in a matter of hours, exposing the surface to intense ultraviolet radiation. Crops could fail, marine ecosystems could collapse, and many species could face extinction. While such an event would be rare, the Sun has been active for over 4 billion years, and in that vast span of time, it may have produced flares and outbursts well beyond anything humans have yet observed. There is also the slow but inevitable truth that the Sun itself is changing. Over the next hundreds of millions of years, it will grow hotter as it burns through its hydrogen fuel. This will cause Earth's climate to warm, oceans to evaporate, and the atmosphere to become thicker with greenhouse gases. Eventually, ultraviolet radiation will break apart water molecules in the upper atmosphere, and the hydrogen will escape into space. This gradual drying will make Earth's surface more and more like Venus or Mars, regardless of human intervention. These possibilities show why comparisons to barren worlds matter. Mars teaches us about the loss of magnetic protection. Venus teaches us about the runaway effects of heat and a dense, toxic atmosphere. Both remind us that planetary habitability is fragile, and that the Sun can be both life's greatest ally and its most relentless adversary. As long as we understand these limits, we can better prepare for a future where survival depends on more than just the warmth of the morning light. In July of the year 2012, a massive eruption surged from the surface of the Sunday. It was a coronal mass ejection so powerful that scientists later estimated it could have rivaled the Carrington Event of 1859. For 2 days, this wave of charged particles and twisted magnetic fields hurtled through space at millions of kilometers per hour. The only reason the world did not descend into chaos was timing. Earth had passed through that exact region of its orbit just days earlier. In other words, our planet missed a direct hit by a cosmic hair's breadth. If the timing had been different, the story would have been very different. The first sign would have been a blinding burst of X-rays and extreme ultraviolet light reaching Earth in just over 8 minutes. Radio signals would have faltered. GPS devices would have begun showing strange errors. High-frequency communication used by ships, aircraft, and military units would have been drowned in static. Within hours, the real danger would have arrived. The coronal mass ejection would have slammed into the magnetosphere with unimaginable force, compressing it closer to the surface. Power lines across the high latitudes would have begun humming with induced electrical currents far beyond their safe limits. Transformers the size of small buildings, some weighing hundreds of tons, would have overheated and failed, one after another. In places like North America and Northern Europe, entire grids could have collapsed within minutes, plunging tens of millions into darkness. Without power, water treatment plants would have slowed, then stopped. Fuel pumps at gas stations would have gone silent. Refrigerated food in warehouses and homes would have begun to spoil. In hospitals, backup generators would have kept life support machines running, but only as long as their fuel lasted. Satellites used for weather tracking and navigation would have been bombarded by radiation, their electronics fried or temporarily disabled. Images from space would have faded to static, leaving forecasters blind to approaching storms. In the skies, airliners flying long routes over polar regions would have been forced to turn back or divert, as navigation became unreliable and radiation levels rose. Ships in mid-ocean would have lost access to accurate positioning, relying instead on older, slower methods of navigation. Traders on global markets would have watched as the world's financial systems stumbled, Bank transactions and stock trades rely on precise timing signals from satellites, and without them, the entire network would have started to unravel. For billions of ordinary people, the crisis would not have felt like a single dramatic moment, but a steady, creeping unraveling. The first day might have brought confusion, the second, a dawning sense that the outage was not temporary. By the end of the first week, supermarket shelves would have been bare in some places, fuel reserves would have tightened, and communities would have been forced to improvise for survival. In such a moment, resilience would have depended on more than technology. Neighbors sharing food, volunteers directing traffic when lights failed, farmers selling produce directly from fields. Human cooperation would have been the invisible infrastructure holding society together when the visible one had collapsed. And yet, this imagined chain of events is not pure fiction. It is an alternate history that came within a sliver of becoming real in 2012. That near miss is a reminder that our margin of safety is far smaller than we like to think, and that relying on luck is a fragile way to run a civilization so dependent on technology. The cost of complacency, if the sun decides to aim at us next time, could be far greater than we are prepared to pay. It is strange to think that our entire way of life rests on something as distant and untouchable as the Sunday. We wake up each day trusting that it will rise, bathe our planet in light, and keep the delicate balance that makes Earth habitable. Yet hidden in that trust is a vulnerability few truly consider. The sun is not a constant, gentle presence. It is a living, breathing star, capable of quiet beauty, but also of unleashing storms powerful enough to rewrite the story of human civilization in hours. The day the sun almost erased life was not some ancient event buried in deep time. It was recent, it was close, and it was only spared from becoming a defining moment in history by the smallest twist of orbital timing. Scientists who have studied that near miss understand that it was not a one-off, freak occurrence. It was part of a natural cycle, a cycle that will, eventually, line up again with us in its path. What makes this reality unsettling is that we are more exposed now than at any point before. When the Carrington Event struck in the 19th century, humanity did not have a network of power grids stretching across continents. We did not have satellites orbiting overhead or a global economy tied together by digital transactions. Our survival did not depend on invisible signals streaming between devices. Today, it does, and the same kind of solar storm that once only lit up the night sky in spectacular auroras could now cut those signals off in an instant. It is worth asking what would happen if the sun's next great outburst arrived tomorrow. How many people could access food and water without the systems we take for granted? How many hospitals could keep patients alive if generators ran out of fuel? How many of us would even know where to turn if our phones went dark, our GPS stopped working, and the voices of the world fell silent? These are uncomfortable questions, but avoiding them does not make the risk disappear. In every field of science, from space weather forecasting to electrical engineering, there are people quietly working to prepare for that day. They study the sun's patterns, strengthen the resilience of our grids, and test backup systems that might keep critical services running. But there is only so much they can do without the will of the wider world to act. Preparedness is not just a job for governments or scientists, it is a responsibility that belongs to all of us. You may never have thought about storing a small supply of food and water for an emergency. You may not have considered how you would contact family if mobile networks failed. But the truth is, history has already shown us that the sun is capable of changing everything in a single moment. We have been lucky before. That luck will not hold forever. So here is where the conversation opens up to you. How prepared do you think you are if the next great solar storm arrives in our lifetime? What simple steps would you take to safeguard yourself and those you care about? Share your thoughts in the comments, because the more people talk about this, the better our collective chance of adapting when it matters most. And if you want to keep exploring the hidden forces that shape our world and our survival, make sure you subscribe and join us for more deep science stories. Every episode takes you deeper into the mysteries of the universe, not to frighten you, but to remind you of the wonder, fragility, and resilience of life on this small, bright planet orbiting a restless star.